foundations of the quantum mechanics, going through all of this, we understand translational function, vibration of the system. Now we finally apply to our chemical system. The first chemical system we started is just one electron atom or ions. Now we formulate the wave functions for those atomic orbitals that we learned when you take the JChem or your AP in chemistry. So those one electron wave function for the electron in an atom really is the wave function for those atomic orbitals. Alright? Now we say that you can link to different atomic orbitals, as you know, from the principal quantum number orbital, angular momentum quantum number L and the L, and how we can link to shells in different orbitals. Now so far we show you a couple of examples. We will show you a couple of examples. The first example we show is those s orbitals when L equal to 0, and you plug in as the angular component of the wave function. It is a constant, so therefore that allows us to that it has a spherical shape. All right, so we introduce the boundary conditions, so on and so forth. And then the one thing we ended in the other lecture is calculate the probability. Probability at a particular location. Right, at a particular point of the space. By the foundation of quantum mechanics is a probability density at that point. Alright, now they can be denoted by x, y, z or whatever. You know, if you just have one system, you have one system variable. And then you time the volume, the small volume in that range. Now how are we going to do it? So if I really want to calculate it, right, so you have x, y, z. Let's say you only have one particle in one system, and the particles is located here. This is your position vector. Then at that location, what is the probability to locate the particle at that location with a very small volume of d tau? And that's the expression. So you have the square modulus of the wave function represent that system at that small volume at that location. Now, because of the unique aspect of the s orbitals, that only actually depends on the radius. At constant radius, at all theta or y angles, the wave function is exactly the same value. So therefore, we can also approach for the calculation of the probability in a different way of thinking. Now, how do we think about it is, all right, now, what I was going to say, this is universally true. No matter what system you're looking at, you can always do it that way. But because of the spherical shape of your s orbitals and your y 0, 0 for the s orbitals equals to a constant. So therefore, you can approach to the probability in terms of a calculation. So you think the system a particular radius, and then you can calculate the thickness of the dr, and from there. And that's what we put it here. So we talk about it. So you can think about the probability finding an electron anywhere between two walls of the spherical of the thickness dr and the radius. You can think about the probability to locate that electron at a particular radius with a very small thickness. Now how I'm going to do that? Alright, so you can approach to locate the electron in the s orbital in that fashion. Alright, now how are you going to do that? Then we need to figure out what the volume. So we're thinking about a particular radius within a small dr. Then the d tau will become the surface area of the sphere at that radius. You guys agree? And then your time the volume of the shell, which is the dr. So that is your volume. So therefore, your probability. So instead of to calculate the probability at a particular point, represented by x, y, z, we can also calculate the electron in the s orbital at a particular radius to the nucleus within that small thickness of dr. So you can approach to think about calculation of that. So you have a nucleus, what will be the probability if the electron is that radius away from that, or that radius away from that. So that's basically what we're thinking. Then the probability would be same. Your square modulus of your wavelength, the wave function, and then times the volume 4 pi r squared and dr. So those wave function should be your s orbitals. Right? So that's one way we can say you can calculate the electron in the s orbital at a particular radius. You can think about it that way. All right, if you look at this way, then what you can do, this is another density, so you still have the density times the volume, except the volume now we're looking at a particular sphere within a certain thickness. So you're looking at the shell with a certain thickness. Okay, in that regard, then what we can combine these two terms together, the square modulus of the wavelength times the 4 pi r. We can find that we group those two together and we make a new function. That is the radial distribution function. So it's a capital P. All right, we use a lowercase p to indicate the probability. So that depends only on the variable r, that's your s orbital. The s orbital wave functions has no dependence in the angular theta or phi. You guys agree with that? So therefore, the distribution function is defined as the square modulus of the wave function times the 4 pi r squared. All right, so then you can rewrite your probability in terms of your radial distribution function, PR times the volume dr. Okay, so when you do this, this gives you the probability to locate an electron at a particular radius. Calculation of this will allow you to understand the probability at a particular point. Here will allow you to locate a particular radius, which is cool because the s orbital is spherical looking. So you just want to know a particular radius, what kind of probability to locate that s electron, because the nature of the spherical shape of the s orbital. So we are interested in that fashion. Are you guys following me okay on this? All right. All right. So this is really nothing fancy. So that is your distribution function. All right. Now we have s orbitals. Give me some examples of s orbitals, guys. 1s. What else? What else? I can't have an infinite amount of s orbitals. What else do you have? 2s and 3s, and keep going. So I said it geometrically, you want to use n and s to represent. Now to make a point, make an example, we can choose the one s as an example. Okay, so let's do a specific calculation for the, let's see, using the 1s, okay, as example. Okay, now, can we come up the distribution, radial distribution function for the 1s orbitals? Now, the radial distribution function for the 1s atomic orbital, it is your square modulus of 1s atomic orbital times So in that case, what is the wave function for the 1s orbital? It's a product of the two components, right? The angular component and the radial component. Now, what is the angular component for this? Do the notation, guys. The angular component for the 1s orbital. So 1s means free quantum number is 1, 0, 0, right? So that's your N, L, and L. So if I wanna, that's what we do, separation of variables. So you're going to have the radial component. Yes. And then you times the 4 pi r squared. Okay. Now, I can pop that slice up for you guys. The angular component, the y00 for the s orbital, that equal to a constant. What is this value for? 1 over root. 1 over 4 pi, right? Very good. Now, are those a real function or not? If they're real function, then the square modulus is really equal to what? Each of those squares. You can remove the operation. Any questions on that? Okay, now, since the y00 is a constant, y squared, I'm only telling, so can I cancel this out? The angular component is 1 over 4 pi, we times 4 pi on the other term, it cancels out. So therefore, what you really have, guys, is, for the 1ss is your, of course, the radial component of the wave function depends on the variable of r times the r squared. That is your exact expression for the radial distribution function for the 1s orbital. Now, if I have a mathematical expression, I'm happy because they can allow me to derive a lot of things. So this is a radial distribution function that gives you the density, or allow you to evaluate at which radius, what kind of probability. Okay, now what I'm asking you, can I calculate the most probable radius for the 1s orbital? How should I do that? Huh? Most probable means what? The maximum? What is the most probable? How do we calculate how do we approach that from the mathematical perspective? You said derivative? What derivative should we do it? Ryan? Did you say derivative? Derivative of which function?
The one we write down there.
Yeah, so this is tell you the information at which radius, right, related. So you're gonna do the derivative of the radial distribution function. That's halfway done. What happened afterwards? That equal to 0. Right, so that allows you to say most likely where the 1s electron will be located, the higher probability, a particular radius. Because the electron can go from 0 to infinity, so now through the radial distribution function, this allows us to evaluate what is the most likely radius to find the 1s electron. Okay, now, so I have this equation right here for you, and then you can know if it's a hydrogen atom. You guys can go home for hydrogen atom. Right, so you need to know what kind of system you're looking at it, so that allow you to have exact radial function, so that allow you to do the derivative, set equal to 0, and locate that radius value. Okay, right. Right. So it's really cool in terms of that we can calculate the probability at a particular point. But the s orbital, they are spherical shape. And as long as you're choosing a 1r value, the wave function is exactly the same at all theta and phi angles. So therefore, allow us to even evaluate at what radius to locate that 1s. Okay, all right. So you can have two ways of thinking about this. All right, now, when you have a mathematical equation, then you can dive in more, right? So this is exactly what we talk about here, except when I plug in the R function here. So radial distribution function equals R squared times the radial component of the wave function raised to the power of 2. And then you can plug it in the functions, and this is your expression. Now, if this is the expression, when R equal to 0, what would be the value for the radial distribution function? What would be the value for the radial distribution function?
0.
Huh?
0.
0. Why? Because you have a square term right here. So R is 0, the whole thing vanished to 0. So therefore, the probability to locate the electron, when R equal to 0, what does that mean? Where's the location of the electron? So what does that tell you? There's a 0 probability to locate that electron at the nucleus. Have you been thinking about this? I can make it as complicated as I would like to. Okay. Now think about it. What about the wave function at R equal to 0? Huh? Is it the maximum, minimum, or I don't know? The wave function. The wave function for the 1s orbital at R equal to 0. And that is the maximum value. Why is that? Because it's an E exponential decay. It's an exponential decay. You guys all follow me, okay? The wave function is an exponential decay with respect to the radius. So when the radius is smaller, the wave function itself has a maximum value. But at the nucleus, the probability to locate at the nucleus is what? 0. It's because of the traffic. All right. So that we can derive it. So therefore, you're not going to find the S electrons at the nucleus. All right. Now, if we can take it, we have an expression. So if it's R approach to infinity, if R approach to the infinity, guys, you guys all love math, right? Like me. So if you have this mathematical equation right here, what you have is you have the terms, guys, that are related with R squared, then you have the exponential decay. So when R goes to the other end of the extreme, goes to the infinity, now what happened? The R squared will go to infinity. How about the E function?
0.
It's going to will be really, really small. Do you guys agree? Now you have to weigh in. One is larger, the other one is smaller. What would happen? And then you can think about it. There's a dominate. There's one term going to dominate in that case. Which term going to dominate at the R approach to infinity? Is the exponential decay part. You can try. You guys can go home. Just do it. What are you gonna do? Just plot the R with the E, see what it look like, and then plot the with the R squared and see what it look like. Okay. So therefore, the probability to locate that electron in a larger radius is also close to 0. All right, now what about in between? So you're talking about the 0 and the infinity. Now the R can be from 0 and infinity. In between, then you can have, just like you said, you're going to have an increased component due to the R squared. You have a, now let me draw this, see if I can draw this. I have increasing, no, that can happen. Increasing component of this, but you have a decreased component of that part. So therefore, you're going to have a maximum at some places. That's what the most probable radius as we just discussed. You guys follow me, okay? All right, okay. All right. Okay. And this is what the radial distribution function looks like, as I just said. 0 at R equals to 0, and then you're going to have these modulations due to the R squared, the E function. You're going to have an increasing component because the R squared dominating at this range, and then you have a balance between the R squared and exponential decay, and you have a maximum value. After that, the exponential decay dominates, and that's why the decreasing is as R approaches infinity, then the radial distribution function equals to 0. So if you take a quick look at this, what is it peak at?
1.
What is the peak at to the radius of it? So it looks like the radial distribution function has a max if you just look at the curve eyeball it. At what radius value, guys?
1.
Huh?
The 1.
Just eyeball this. We don't have to be everything to be something. 1? What do you mean 1? Oh, 1 is referred to, yes. 1 is multiplied by this factor, right? They make those everything to be simple with substitution, but they also have a unit in the x-axis. 1 unit of what? Z R over A naught. Very good. Very good. Now, for hydrogen atom, what will be that value?
A naught is for R.
Huh? So the radius equals to 1 unit. All right, so basically the Z equal to 1, so the R equals to A naught. So what is the A naught value? I think this is probably
Constant.
maybe the second time I'm telling you what the A naught value is.
It's 5.27.
Now you guys know why it is 52.7. We also call that as a Bohr radius. 52.7 is the most probable distance for the 1s electrons in the hydrogen atom. So most likely you're going to locate that 1s electron in the hydrogen atom at what location? 52.7 away from your nucleus. Okay. Right. All right. we say those are the one electron system are the atomic orbitals. So we went through n equal to 1, L can only be 0, M sub L can only be 0, and that is the wave function 1, 0, 0, corresponding the wave function to the 1s atomic orbital. Right? So that's why I say those one electron system is really formulate the wave function for those atomic orbital. Now let's go for n equal to 2. So we say when n equal to 2, how many L value do we have?
Equals 2.
2, right? What are they?
0.
L equal to 0, M sub A equal to 0, then there's 0, 2, 0, 0. That is the wave function for one electron system means 3 quantum numbers, and that is a direct correlation for your 2s orbital. Okay, so you already know. If somebody asks you about the 2s orbital, you say, do you want to sit down and challenge me about it? Let me go through a functional equation and show you exactly what the mathematical equation, not just a 2s bracket, right? It's just a square bracket, that's your 2s. You can tell them exactly what it is. What else do we have? Now we have the second shell. This is your K shell, this is your L shell, right? So your second shell, you can have L equal to 1. This is your s orbital. When L equal to 1, what orbital are we looking at it? P. Very good. And then what do you have? You're going to have 3 M sub L values, right? Now you're going to have 3 wave functions, which one is 2L0, 3 quantum numbers. Principal, orbital, magnetic, 2, 1, 0. All right, now you have all right, where are we going? Where are we going? All right, now for the p orbitals, what do we know for the p orbitals, guys? We're going to have, where should we write? We're going to have px, py, pz, right? I saw you guys are doing like gym stuff right now. So are you going to show me the dumbbell, the John look like shape for your p orbitals? Can you draw one of the p orbital shape? A boundary surface for the p orbital. Why don't you guys draw it? I give you a little break. Just draw one of the p orbital boundary surface. Just separate them. Just separate them.
Then we've
Put the
got some.
axis on it. Put the axis on it. You draw the south, see what it looks like.
Where?
In the same shape. Can we just draw one together?
Yeah.
So, right. Now, what I learned to draw in 3-dimensional space, the things is below the plane, use a dash. I don't know how you guys will talk, but that's how I always talk. All right, now when we look at it, if I draw one of them, is it looking like this? What is this? What is this one? That's your PZ, right? So that's one of them. And then you equivalently do it for the other 2 of them. All right, and then you can say, okay, got it. Now we have those 3 wave functions. How are we going to represent those 3? Right? We say the 100 is a direct 1s, 200 is direct 2s. Now I have 3 wave functions for 2p right here. I have exact mathematical expression for each one of them, but how I'm going to correlate to the px, py, and pz. Right, the correlation, guys, is a little trickier. So when the m sub l equal to 0, the 2, 1, 0 is a direct correlation to the 2pc. All right, now if I do a linear combination of those two, what is the other fancy words for linear combination?
It's an eigen.
We learned this in Oxford. Very fancy words.
Eigen.
We call it it's the same. A superposition of these two with plus and minus. They're exactly the same. The magnitude for the m sub l, except the m sub l only varies by the sign. One is positive, the other one is the negative, right? That will give you, so it's not a direct correlation to px and py. This will give you px and py. Now, what is a linear combination? Okay, so if I have A and B, right? Just simplify it. I have A and B. If I do a linear combination, mathematically, how do I do it, guys? Mathematically, you have two ways of doing it. Any guess? Linear combination. All right, so one is the minus, the other one is plus. So in that regard, we're going to go to the math in a minute. You have two functions. You do a linear combination, add them together, you have one function. You have a do minus combination, you have the other function. So therefore, do a linear combination, you can generate a new form of two functions, one corresponding to px, the other corresponding to the py. So by saying that, I want you guys to understand what the nature of those orbitals, what the origin that comes from, and then we can dive in the math. Are you guys all following me okay? So for the s orbital is the direct. But for the pz orbital is when the m sub l equal to 0 correlates directly. But the px and py are the linear combination between the m sub l plus minus 1. All right, so still you have three quantum states corresponding to the three sets of px. Okay, here we go. Now we will use, right, p, you also can have np orbital. Right, so you can have 2p, 3p, 4p, 5p, whatever you would like, and to make a point, we will use 2p orbitals as an example and show you why a shape like this. All right, now let's give it a sign. Okay, can you guys come up with an expression for the 2pz? If I say 2pz, That means n equal to 2, L equal to P orbital, so L equal to 1. Then the Z to be Z means M sub L equal to 0. So in that regard, based on the tables we already have, then we know the 210 wave function that depends on R, theta, and phi, right? And the wave function for those one electron system is the product of the radial component, which is represented by N and the L as a variable R. Then you have the angular portion, which depends on the L and the M sub L, depends on the two angle variables. All right, then we show you in the table what will be the radial component function, what will be the angular component of the function. So if we look it up, that is your check. So like this. So you have the radial component right on the table. Then you have the angular component. Angular component 1 is constant anymore if you look at the 1, 0. Oh, good. Okay. All right. Now, you know, rho is just a substitution for this expression to look simpler. But rho is substituted for the radius, so we need to plug back in. All right, so the rho equals to that's just what is defined. Rho equal to 2 times z atomic number times the variable r, radius, divided by principal quantum number n times the a constant, A0, they're close enough. All right, now for this particular one, what is n here? We said we're using, very good, we said we're using the 2p, right? So therefore n is 2, okay? So immediately, if that is the case, what do we see, guys? 2 here. So the rho equals to z over a times r. This is your constant times your variable r. Any questions on that one? Okay, if it's not, when you guys finish writing, look at me so I know you guys are ready to. Is it all good? All right. I didn't know I can write this fast. Yeah. All right. So now what can we do? Can we substitute the rho here with the radius? Right here. This guy substituted here. Also, the rho will be substituted right here in the e function. Okay. Now I want you guys to go further step. Not just a substitution. Furthermore, all right. Combine the constant. I have a z over a here raised to 3 over 2, the power of 3 over 2. Now what did the rho carry? Z over 2. So if I combine this together, what do I have here? Come on, I need you guys. What do I have here? Who said it? Okay, thank you. Alrighty, so you're gonna have 5 over 2, then this become R. Alright, now what I'm having is a substitution for the rho here with this guy. So yes? I didn't fancy. All I just did is just plug them all in. Okay, and with the given conditions for the principal quantum numbers.
Wait.
All right.
Oh, I see.
Now I would like to call attention. All right, remember the conversion between the spherical coordinates and Cartesian coordinates, right? You guys still remember that?
Oh,
Pretty good. If you remember, I want to ask you, when I have r times cosine theta, what does that equal to? I can give you three choices, x or y or z, which one?
X.
Is it the cosine theta, is it the x? Z. So I have, who's that x? Okay. Z, how many of you guys agree with Z or X or Y? Huh? That's just a definition, the conversion, right? The conversion between the R, theta, and phi to X, Y, and Z. Now I want to tell you R times cosine theta equals to variable Z in the Cartesian coordinates. Okay, you may ask, where am I going here? Alright, now, if you take a look at this, what do you see here? Constant, and also constant, and then you have this function that depends on the variable of R. So therefore, mathematically, I could just group them into the other function, group all of this as the f function depends on the r, then times what? Variable z. Okay, we're almost there. All right. Now, if this is the wave function 2, 1, 0, can you represent it by a function? Depends on the variable r and also a variable z. Based on that mathematical function, what conclusions can we draw, guys? And that's the whole point, to come up with the shape as it is. It's really based on the description of the mathematical equation that we put into the descriptive words. But the descriptive words really coming from that mathematical foundation. So if I have something like this, what can you draw, guys? All right, let me ask a simple question, right? So this is the mathematical function, depends on the r, depends on the z. One easiest way is, what if z equal to 0? Then what do you have? Yeah, what do you have? Huh?
0.
Okay, now if that is equal to 0, so what does that mean? Is that true? Is
Yes.
that true?
Yeah.
Right. Now you have this mathematical function that you put into your calculator, and you draw the shape, and you capture the 90% of the electron. That's why the PZ orbital looks like the way it is. All right. Now you kind of sort of thinking about what is PZ. It has a z variable right here. Like if you do a px and py, it will have exactly the same formula. And by plotting that, you will see the shape like this. Okay. Are you guys want to try one of the linear combinations to see if I have something like this? Yes?
Sure.
Alright. So I just showed you mathematically what would be the 2pz orbital is represented. This is really the wave function is 0 everywhere in the xy plane, where z equal to 0, and then we can call it, we can have the node, when you're passing through a point, we say that is a node. But then we can passing through as a plane, that is give you 0, then we call it, it's a nodal plane, right? And the wave function changes the sign when you go from one side of the plane to the other. So basically, not only that you know it looking like the shape as you know, but also have the amplitude for the, now you have a mathematical equation, so therefore you have an amplitude. So therefore you are going to have positive values and switch to the negative values as a mirror image for the xy plane. Does that make sense to you? So therefore you will have, when you draw those p orbitals, it has a positive above the xy plane and the other one is negative. Not only just draw the shaping. Okay. Alright, now how are we going to do the 2pz? And we did the 2pz, now how are we going to do the px and py? It's the linear combination of those two, as I said. You have those two exact wave function, and you do a linear combination. Now, of course, it's a wave function to represent the 2px and 2py, so therefore that wave function has to be normalized. So therefore, what else do you have? You have a constant. So, showing you here, the idea that you have a linear combination of two of the wave function in the minus form that form the 2px. In the plus form, it forms the 2py. But the wave function to represent the wave function 2px or 2py has to be normalized. So therefore, in addition to the linear combination or superposition, you will have a constant. And the constant is different for the px and py. So if you already know the 2p plus 1 and 2p minus 1, do this mathematical operation, you're going to come up the wave function for the 2px and 2py. Alrighty, now if I can borrow 30 seconds, now for the d orbital. For the d orbital, you will have those 5, and when L equal to 2, you will have 5 m's of L values. You do manipulation that form those 3 d orbitals. Okay, I think I concluded all the discussion, and we'll see you on Wednesday.